Next topic, that is digital electronics and logic gates. Now see, if we think about the voltage current, right, then there are two types of signals. One that is called analog signal, another one that is called digital signal. Analog signal means such a signal in which voltage attain any value between maximum to minimum. So see here in the figure, the analog signal is represented. So value of the voltage that can be any one between maximum to minimum, maximum to minimum. It can attain any value. That type of signal, that is called analog signal. And between maximum to minimum, it is a continuous signal. Means each and every value it can possess. Okay, so that type of signal, that is called analog signal. Now if we think about digital signal, then now digital signal, that is pulse waveform type, in which the voltage will attain only two values, either the maximum value or minimum value. So to represent this two stage of the voltage, one value that is maximum one, another value that is minimum one. So to represent this particular situation, we use binary number system, because in binary number system we use only two digits, 0 and 1. So for digital signal, when we use 1, it implies that the value of the voltage that is maximum, and that is say 5 volt. Normally logic gate circuits are operated at 5 volt. So when maximum voltage is there, 5 volt, then it is considered as level 1. And when the value of the voltage that is 0, that is lower value, okay, then that is treated as 0 volt. Okay, so in this way the digital signals are represented with level 0 and level 1. In that, only two possibilities are there. Voltage will attain either the maximum value or the minimum value. So here see the waveform for digital signal is represented. It will attain either the maximum value or the minimum value. Clear? In between these two, any value will not be possessed by it. So these type of signals are called digital signals. Clear to all of you? Now see, logic gates. Okay, logic gate, that is nothing but a digital circuit which follows certain logical relationship. And these logic gates are with one or more than one inputs, but only one output. But only one output is there. Okay. Now they are generally known as logic gates because gates control the flow of information. Okay, and therefore are termed as logic gates. It also follows some logical relationships and it controls the information, or we can say flow of information. There are 5 types of logic gates: NOT, AND, NOR, and NAND. NOT, AND, OR, NAND, and NOR. Order में लाइए तो. Okay. Now see here, for each logic gate we have specific symbols. So each and every logic gate will be represented by its symbol only, and its working, that will be represented by a truth table. That truth table is nothing but how you will get the output or what you will get the output for different combinations of inputs. That representation, or we can say one type of observation table, that is called truth table. Clear? So in truth table, we will see this thing. If we get output, then it will be represented by level 1. And if we don't get output, then it will be represented by level 0. Clear? Now let's discuss different logic gates. Now see here. First NOT gate. Okay. So this one is most basic gate. It have only one input and one output. Each and every gate have one output, but inputs will be different one. So this particular gate have only one input. Okay. The circuit symbol, that is as shown in this figure. Clear? This one is the circuit symbol of NOT gate, and this one is its truth table. Right? Now, see how to understand this particular truth table. So truth table suggests this thing: when your input here A, that is 0, it implies that to input 0 volt is given, then in output you will get 5 volt. So when input level is 0, your output level, that is 1. Okay. And when your input, that is at level 1, it implies that in input if you give 5 volt, then your output, that will be equal to 0. So this one is the working of NOT gate. Okay. And here, just 1 minute. Now see here, we discuss this thing. For NOT gate, only one input is there and one output. Okay. And the working of it, that we represented here. If input is at 0 level, you will get output at 1 level. It implies that if 0 voltage is applied to input, then you will get 5 voltage in output. And if input level is 1, it implies that in input 5 volt is given, then output will be 0 volt. Here, this one is also represented like this. If input is absent, then output is present. If input is present, output is absent. Okay. Now, let's understand the working of this NOT gate with the help of one electrical circuit. આ વસ્તુ ટેક્સ્ટમાં નથી આપી, પણ તમને સમજવા માટે એક આ સર્કિટ મેં લીધી છે. ઓકે. Suppose we have a bulb which one is connected with the battery as shown in this figure, and parallel to the bulb switch is there. Ideally, we can consider switch have 0 resistance. Okay. Now suppose this particular switch, that is off, it implies that here there is no contact between these two terminals. It implies that now this is the open circuit. When this one is open circuit, it implies that the current from the battery, that will flow through this particular bulb, and bulb will glow. So we can say this thing: for this electrical circuit, if switch is off, then bulb will on. But if we switch on this one, then what happens? This particular branch have nearly 0 resistance, so almost all the current will flow through this one, and negligible current will flow through the bulb, so bulb will not able to glow. It implies that now we can say when the switch is on, bulb is off. Input is absent, output is present. Input is present, output is absent. Clear to all of you? And now see, no doubt, these two table and the symbol is the same thing which I represented here. But the important thing which I want to represent here, that is this one. Symbolically, the output of NOT gate, that is represented as Y equal to A, and this symbol of bar that we have to place over A, and this one is read as Y equal to not A. This one is read as Y equal to not A. એટલે આ ટાઈપનો not A એટલે કે A બાર આવો સિમ્બોલ જ્યારે ક્યાં યુઝમાં આવે ને તો સમજી જવાનું કે જે ઇનપુટ છે એનું ઓપોઝિટ થઈ જાય છે અહીંયા આગળ. બરોબર? એટલે કે ઇનપુટ પ્રેઝન્ટ હોય તો આવી રીતના બાર કરીને જો આપણને આઉટપુટ આપ્યો તો એનો મતલબ કે એનું બિહેવિયર નોટનું છે, આ નોટનો સિમ્બોલ થાય છે આવું. બરોબર છે? એટલે આ વસ્તુ ઇમ્પોર્ટન્ટ છે. જો અહીંયા આગળ ખાલી આઉટપુટ y લખ્યો છે ટેક્સ્ટમાં, એકચ્યુઅલી આઉટપુટ y ધેટ ઇઝ a બાર સિમ્બોલિકલી આવી રીતે આ રિપ્રેઝન્ટ થાય છે. Clear to all of you? Any doubt in this one? Now OR gate. OR gate have two or more than two inputs, but only one output. Okay? And the circuit symbol that is as shown in this figure, and its working that is represented here with this truth table. So in that, if both the inputs are absent, means at 0, 0 level, output is 0. If A is 0, B is 1, then output is 1. If A is 1, B is 0, output is 1. If A is 1, B is 1, output is 1. It implies that now we can say this thing for OR gate. If either OR input or both the inputs are present, then we will get output. જો કોઈ પણ એક અથવા તો બંને, here B is present, here A is present, and here both A and B are present, then we are getting output. So we can say this thing, if either or both inputs are present, we will get output in OR gate. Clear to all of you? Now see here, to understand the working of this one, consider again one electrical circuit. See, as shown in this particular figure, consider a circuit in which bulb is connected with the battery through two keys, K1, K2, and these two keys are connected parallel to each other, and this parallel combination of keys, that is in series with battery and bulb. Now see here, suppose we think about the situations of keys, or we can say switches. So K1, K2, and what is the result in output means bulb will glow or not. Let's try to understand this thing. Suppose initially both the switches are open or both the keys are open. It implies that current will not be able to flow through the bulb. So if K1, K2, both the switches are open, bulb is off, it implies that here see both the inputs are absent, output is absent. Then after K1 that is open, but K2 that is closed. So current will flow through K2 to bulb, and now bulb will glow. So now we can say when K1 is open, K2 is closed, bulb is on. It implies that A is absent, B is present, you are getting output 1. Then K1 is closed, K2 is open. Then also current will flow in the circuit through K1 and bulb will glow. So we can say bulb is on. So A is present, B is absent, then also you are getting output. if both the keys are closed, then also you will get the current through the bulb. Clear? And bulb will glow. It implies that A is present, B is present, and you are getting output. So we can say either or inputs or both the inputs are present, then we will get output. Or in other words, we can say for OR gate, if all the inputs are absent, see this first thing, all the inputs are absent, then and then only the output will be absent, or in any other case, you will get output. Clear to all of you? So this one is the working of OR gate. And see, in equation, the working is written as output Y, that is, symbolically it is written as A plus B, and is read as output Y equal to A or B. આ symbol થી એનું working equation ના form માં લખાય. Clear to all of you? AND gate has two or more than two inputs, and the working of it, that is like this: if all the inputs are present, then and then only we will get output. Otherwise, if any one or all the inputs are absent, output will not be obtained. This is the circuit symbol of it. This is the truth table for the working of AND gate. See, input A, input B, and output Y. If both the inputs are absent, output is absent. If A is absent, B is present, output is absent. If A is present, B is absent, output is absent. If both A and B are present, then and then only you are getting output. Now understand this thing with the help of electrical circuit. Suppose we have electrical circuit as shown in the figure, in which the bulb is connected with the battery through two keys in series. Now see here, if these keys or switches K1 and K2 both are open, circuit will not be completed, current will not flow through the bulb, and bulb will be in off mode. If K1 is open and K2 is closed, then also circuit will not be completed and bulb will be off. Then if K1 is closed, K2 is open, then also bulb will off. And if both the keys are closed, then the circuit will be completed and the current will flow through the bulb and bulb will on. So if all the inputs are present, then and then only you are getting output. In any other case, you will not get output. And the working is represented in the form of equation like Y equal to A dot B. It is read as Y equal to A and B. Clear to all of you? Now NAND gate. Actually, NAND gate, that is the combination of AND and NOT gate. When AND gate is followed by NOT gate, then the circuit prepared, that is called NAND gate. That is called NAND gate, that is exactly opposite to AND gate. In AND gate, when all the inputs are present, then and then only we get output. In any other case, we will not get output. So opposite to it, for NAND gate, if all the inputs are absent, then we will get output, and either or the input is absent, we get output. But if all the inputs are present, we will not get output. Okay, so that is the working of NAND gate. Now see here, this one is the circuit symbol of NAND gate. So in that, this one is the AND gate, and this circle here placed on the AND gate. that is represent the NOT gate. So this combination of AND and NOT, that is the NAND gate. So it's truth table. Input A, B, output Y. So inputs A and B, both are absent, 0, 0, then output is 1. A0, B1, output 1. A1, B0, output 1. A1, B1, output 0. Okay. હવે જો જ્યારે તમને આવી રીતના NAND, NOR હજી આના પછી આવશે એ બધા આપ્યા હોય ને તો વચ્ચેનું ઇન્ટરમીડિયેટ સ્ટેપ છે ને એ ઓલવેઝ તમારે લખવું. આને રિલેટેડ જ્યારે પ્રોબ્લેમ્સ આપણે સોલ્વ કરીશું ત્યારે બી હું તમને બતાવીશ કે બને ત્યાં સુધી ઇન્ટરમીડિયેટ સ્ટેપ છે ને તમારે લખવું છે, એટલે તમને ક્યારેય આમાં લોચા નહીં પડે કે આઉટપુટ આપણને શું મળે છે. બરોબર. હવે જો એકચ્યુઅલી કેવી રીતના ફોર્મેશન છે તો એન્ડ ગેટ, એન્ડના ઇનપુટ્સ A and B, output of AND, that is input of NOT, and then finally you are getting here the output. Okay. હવે AND નો આઉટપુટ જે છે એ ઇક્વેશનના ફોર્મમાં તમે A ડોટ B લખો છો, પછી નોટ આવે તો નોટ માટે આપણે બારનો સિમ્બોલ યુઝ કરીએ છીએ. તો જો ફાઇનલી યોર આઉટપુટ Y, that is નોટ એટલે કે બાર A ડોટ B, આ ટાઈપના ઇક્વેશનનો સિમ્બોલ થાય એનો. ઓકે. આ બેને કમ્બાઈન કરીને ફાઇનલ સિમ્બોલ NAND ગેટનો આ બનાવ્યો, આ આપણને આપ્યો છે એ મેં બોર્ડ ઉપર ડ્રો કરેલો બતાવેલો છે. બરોબર. હવે જો ઇન્ટરમીડિયેટ સ્ટેપની જે હું વાત કરું છું એ AND is followed by NOT. તો પહેલા છે ને એન્ડ નો જે આઉટપુટ હોય ને એને ઓલવેઝ ટ્રુથ ટેબલમાં તમારે મેન્શન કરવું, તો તમારે કોઈ દિવસ લોચો નહીં પડે. જો કારણ કે ઓર, એન્ડ અને નોટ એના તો આપણને મોઢે જ હોય છે અને તમે 2-4 વખત વાંચશો એટલે બાય હાર્ટ થઈ જવાના છે. જો ઇનપુટ A, B 0, 0, 0, 1, 1, 0, 1, 1. Now output of AND, that is A and B 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. એટલે એન્ડ ગેટમાં આપણે ડિસ્કસ કર્યું કે if all the inputs are present, then and then only you are getting output. In any other case you are not getting output, or in any other combination of inputs you will not get output. હવે એન્ડ ગેટનો આઉટપુટ એ નોટનો ઇનપુટ થયો અને પછી ફાઇનલી નોટનો જે આઉટપુટ થયો એ આપણો NAND આઉટપુટ થઈ ગયો. હવે તો જો હવે અહીંયા જ ખાલી કોન્સન્ટ્રેટ કરવાનું તમારે. 0 તો નોટ શું કરે, ઓપોઝિટ આપે એનું. તો 0 to 1, 0 to 1, 0 to 1 and 1 to 0. It implies that now finally you can understand this particular one. Okay. So 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Clear? So here you can see this thing. Now for NAND gate, if all the inputs are present, you are not getting output. In any other combination of inputs, you are getting output. Clear? So in this way, you can understand this thing and easily you can remember this thing. Clear to all of you? NOR gate. NOR gate also have 2 or more than 2 inputs, but only one output. And when OR gate is followed by NOT gate, the resultant obtained, that is NOR gate. Okay. So that is the combination of OR and NOT. So here, when we think about its working, then see this truth table for its working. This is the circuit symbol. This is the symbol of OR, and here at output we have to place open circle that represent NOT. So this one is the combination of OR and NOT. Okay. And this truth table represent its working. But let's understand this thing with the help of this intermediate step. First is OR gate, output of OR, that is the input of NOT, and finally NOT gate is giving you the output, which is represented as Y equal to output of OR, that is A plus B, and NOT will give you opposite of it, so here symbol of bar. So we read as Y equal to not A or B. Okay, and final circuit symbol is this one. Now see inputs A and B for OR gate. So first think about OR gate. 0 0 0 1 1 0 1 1. So we know this thing for OR gate. If all the inputs are absent, then and then only the output is absent. In any other combination of input, you are getting output. So here see 0 0 0, 0 1 1, 1 0 1, 1 1 1. Now concentrate here. This output of OR gate, that is the input of NOT gate, and NOT will give you the opposite. So 0 to 1, 1 to 0, 1 to 0, 1 to 0. It implies that we can represent the working of NOR gate like this. If all the inputs are, see this A and B both, all the inputs are absent, then you are getting output. But in any other combination of input, you are not getting output. So this one is the working of NOR gate. And this NAND gate and NOR gate are called universal gates because with the help of the combination of this NOR and NAND, you will get the NOT gate, OR gate, as well as AND gate. એટલે આ બધા બનાવી શકાય આના યુઝ કરીને કોમ્બિનેશન્સ થી, રાઈટ? એટલે આને યુનિવર્સલ ગેટ્સ પણ કહેવામાં આવે છે. Clear to all of you? Any doubt in this one? Example 14.1. Carbon, silicon and germanium have same lattice structure. Y is carbon insulator while silicon and germanium intrinsic semiconductors. Because carbon have the band gap energy that is large one compared to silicon and germanium. Because for all these, the 4 valence electrons are in respectively second, third and fourth orbit. So in carbon, these valence electrons are strongly bounded, therefore it behaves as insulator, while silicon and germanium as semiconductors. Example 14.2. Suppose a pure silicon crystal has 5 into 10 raised to 28 atoms per meter cube. It is doped by 1 ppm, means particle per million. 1 particle per million. Concentration of the pentavalent arsenic. Calculate the number of electrons and holes given that Ni, that is 1.5 into 10 raised to 16 per meter cube. Very simple thing. We have Ne into Nh, that is equal to Ni square, where Ne, that is the number density of electrons, Nh, that is number density of holes, and Ni, that is the number of particles in intrinsic semiconductor. Okay. Now see here, it is given to you pure silicon crystal has this much atoms per meter cube. Okay. So we can write here Ne, Nh, that is Ni square. So Nh, that is equal to Ni square upon Ne. Ni square upon Ne. Now Ni square. So 1.5 into 10 raised to 16 square, directly it is written here. So 2.25 into 10 raised to 32 divided by 5 into 10 raised to 22. See here, total number of atoms are 5 into 10 raised to 28. And per 10 raised to 6, one particle is doped. It implies that in 10 raised to 28, you can accommodate total 10 raised to 22 impurity particles or impurity atoms. And per 1 arsenic atom, you are getting one free electron, and therefore here the number of free electrons per meter cube, that is taken as 5 into 10 raised to 22. And if you solve this one, your answer will turn to 4.5 into 10 raised to 9 per meter cube. Clear to all of you? Example 14.3. Can we take one slab of p-type semiconductor and physically join it to another n-type semiconductor to get p-n junction? No, we already discussed this thing at atomic level. If we think about the interatomic distance, that is of the order of 2 to 3 angstrom, and compared to that the roughness of the surface which are in contact to each other, that is too much larger one, and therefore discontinuity between the atoms during the contact of two surfaces will be there, and therefore we can't form the p-n junction. Clear to all of you? Example 14.4. The VI characteristic of calculate resistance of the diode at A, ID equal to 15 milliampere, and B, VD equal to minus 10 volt. Now ID, that is 15 milliampere, VD, that is minus 10 volt, that is given to you. Now forward bias resistance, that is delta V by delta I, that is V2 minus V1 upon I2 minus I1. Now see this particular graph. From the graph you can write V2, that is 0.8, here V1, that is 0.7. Corresponding to it I2 and I1. So that is 20 and 10, but that is in terms of milliampere. So we have to write 20 minus 10 into 10 raised to minus 3. And now solve this one, you will get answer 10 ohm. Clear? Then after reverse bias resistance, that is V by I. So V, here it is given to you minus 10 volt. And current I, that is, see from the graph, it is 1 micro ampere. Okay, so minus 10 volt upon minus 1 micro ampere, micro, that is 10 raised to minus 6. So when you solve this one, you will get 10 raised to 7 ohm, or simply you can write this one is 10 mega ohm. Clear to all of you? Example 14.5. In a Zener regulated power supply, a Zener diode with Vz equal to 6 volt is used for regulation. The load current is to be 4.0 milliampere and the unregulated input is 10 volt. What should be the value of series resistor Rs? Now see, Zener voltage, that is given to you 6 volt, IL, the load current, that is 4 milliampere. Then input signal, or we can say input unregulated voltage, 10 volt, we have to calculate Rs. Zener current, so IZ, that is equal to 5 into IL, 5 into 4, that is given to you here. So that is 20 milliampere. Okay. Total current through Rs, that is 20 plus 4, that is 24 milliampere. 20 milliampere, that is of Zener current. Okay. And 4 milliampere, that is the load current. So total, that is 24 milliampere. Now potential difference across Rs. So total input, that is 10 volt. Across Zener you are getting 6 volt. So 10 minus 6, that much voltage will be across a series resistance. Now RS, that is V by I, across series resistance you are getting 4 volt, and it is divided by 24 milliampere. So 4 upon 24 into 10 raised to minus 3, and you will get the answer. Clear to all of you? Normally, Zener current that is taken large compared to load current. And normally it is taken 5 times. Normally it is taken 5 times. So here load current is 4 milliampere. So Zener current that is taken as 20 milliampere. Just remember this thing to solve any problem related to Zener. Now example 14.6. The current in the forward bias is known to be more than the current in the reverse bias. What is the reason then to operate the photodiode in reverse bias? Okay. Now see here, if we consider N-type semiconductor, then in that the majority charge carrier, that is electrons, okay, and we can say this thing, the number density of electrons that is greater than the number density of holes. Now here, if we illuminate it by light, then what happens here? Suppose excess electrons and holes are generated, and that is delta N and delta P respectively. So now new number density, or we can say number of electrons, that is N plus delta N, and new number of holes, that is P plus delta P. Okay. So N dash and P dash, that is the concentration of electron hole after the illumination. But here, see, we already discussed here in this part, N is greater than P. Now see, when it is illuminated by light, the electron hole pairs are generated. So in that particular case, delta N and delta P, that will be same one. But see, if we think about the fractional change in majority charge carriers, so fractional change, that is delta N by N for majority charge carriers. For minority charge carriers, fractional change, that is delta P by P, but N is very much greater than P. Therefore, fractional change delta N by N, that is very small compared to delta P by P. It implies that when the fractional change in the minority charge carrier is large one, then due to illumination, easily you can detect that particular current constituted by minority charge carriers, because fractional change is more in that one. And now to detect it due to change in minority charge carrier, we have to use reverse bias, because in reverse bias we are getting the current due to minority charge carriers, and therefore this one is operated in reverse bias mode. Clear?